In the vast expanse of our solar system, one planet stands out for its peculiar dance around the Sun, Venus. This world, often called Earth's sister planet due to their similar size, is in fact quite unlike our home. To begin with, a single day on Venus, a Venusian day, stretches out longer than an entire year on that same planet. Imagine that. One full rotation of the planet taking more time than it takes for Venus to complete its journey around the Sun. What defines a day and a year on Venus, and how do these durations compare to Earth? Let's dive into the intricacies of this extraordinary planet. To start, let's talk about a day. On Earth, we experience one day as the time it takes for our planet to complete a single rotation on its axis. For Venus, this is quite different. A full spin of Venus around its own axis, what constitutes one Venusian day, takes approximately 243 Earth days. This is an incredibly slow rotation. In fact, it's the slowest rate among all planets in our solar system. Now let's consider a year. On Earth, we define a year as the time it takes for us to orbit around the Sun once. On Venus, this duration is much shorter than its day. It takes about 225 Earth days for Venus to complete one full orbit around the Sun, which means a Venusian year lasts only about 225 Earth days. So to summarize, a Venusian day is roughly 243 Earth days long, whereas a Venusian year is around 225 Earth days. This means that on Venus, one day is longer than an entire year. It's as if the planet takes its sweet time spinning once while quickly zipping around the Sun. But why is this so? Why does Venus rotate so slowly? Venus is one of the few planets that spins in a direction opposite to most other planets, including Earth. This backward rotation means that on Venus, the Sun rises in the west and sets in the east. This peculiarity adds another layer of complexity to understanding this planet's unique temporal dance. Imagine what this would mean for life on Venus if it existed. The constant, slow shift of the Sun from east to west and back again must create an entirely different experience than our own. But given Venus's extreme conditions, scorching surface temperatures hotter than Mercury's, despite being farther from the Sun, and an atmosphere so dense that it crushes objects with immense pressure, life as we know it couldn't survive. In this vast universe filled with wonders, Venus stands out for its unusual properties and the questions they raise. How can one day be longer than a year? The answer lies in understanding the unique temporal rhythms of this enigmatic planet. As we delve deeper into Venus's mysteries, each new discovery only adds to our growing curiosity about this extraordinary world. Perhaps one day we'll uncover the reasons behind Venus's slow dance and shed more light on its secrets. For now, the planet continues its steady backward turn, casting a peculiar shadow in the grand ballet of our solar system. Venus's rotation is a peculiar ballet, a dance that defies what we expect from our own home planet. This second rock from the Sun spins in a direction opposite to most others, a phenomenon known as retrograde rotation. Picture it, on Venus, the Sun rises in the west and sets in the east, casting an unfamiliar glow across its scorched surface. The Sun's apparent path across Venusian skies is a testament to its unusual spin. This backward spin isn't just an oddity. It has profound implications on the planet's climate and daily life, if any were to exist there. As the Sun rises in the west, it begins a slow journey across the sky, reaching its zenith around midday before descending towards the eastern horizon. It's a peculiar sight, one that challenges our intuitive understanding of day and night. This retrograde motion is driven by the gravitational tug-of-war between the Sun and Venus's dense atmosphere. Over time, this interaction has slowed Venus's rotation to a crawl, taking 243 Earth days for a single spin. It's easy to picture the Sun peeking over the western horizon, casting its warm rays on Venus's blistering surface. But what does this backward spin mean for life as we know it? If life did exist on Venus, it would experience a day that stretches far beyond our own concept of time. Such an environment poses fascinating questions about the possibilities and limits of life in our universe. For now, Venus continues its steady backward turn, casting a peculiar shadow in the grand ballet of our solar system. As we gaze at this enigmatic world, we are reminded that even within the familiar, there lies profound mysteries waiting to be unraveled. What other secrets might Venus hold, and what can its unusual rotation teach us about the cosmic dance that connects all planets? Only time and further exploration will reveal the full story of this backward spinning world. As we observe Venus from afar, a fascinating spectacle unfolds. The planet's unusual rotation causes the sun to rise in the west and set in the east. Imagine standing on this alien world as it begins its day. The sun has just risen, casting a warm glow across the landscape. But there's something unusual about this sunrise. It's happening in the west. On Earth, we're accustomed to the sun rising in the east and setting in the west, but on Venus, the day begins with the bright orb ascending from the opposite direction. As the sun reaches its zenith, it begins its descent back towards the horizon. But again, this isn't the familiar westward journey we know on Earth. The sun sets in the east, marking the end of a Venusian day. Throughout this bizarre cycle, the extreme conditions of Venus continue to paint a stark contrast with the habitable Earth. The heat on Venus is so intense that metals like lead would be liquid puddles on its surface. Its dense atmosphere causes a significant greenhouse effect, trapping heat from the sun and keeping temperatures consistently high. The thick atmosphere also drives strong winds at high altitudes, reaching speeds of up to 224 miles per hour, 360 kilometers per hour. These winds whip around the planet, adding another layer of chaos to this already alien landscape. As we gaze upon Venus from a distance, it's hard not to marvel at how different conditions can be across celestial bodies in our cosmic neighborhood. The extraordinary properties of Venus's rotation teach us about the delicate balance that allows life as we know it to flourish on Earth, a reminder of our planet's unique and fortunate place in the universe. The slow rotation of Venus is no ordinary celestial dance. This planetary waltz holds the key to understanding the cosmic forces that shape our universe. Venus spins so slowly that it takes about 243 Earth days for a single rotation. This is not merely a peculiarity, but a testament to the powerful interactions at play in our solar system. Scientists believe that this leisurely pace is the result of tidal interactions with the sun over time. Picture this. Just as the moon's gravity pulls on Earth's oceans, creating tides, the sun exerts a similar gravitational pull on Venus's atmosphere. These forces act like gentle brakes, gradually slowing down Venus's rotation. Over billions of years, the sun's influence has led to this sluggish spin, a delicate ballet of celestial mechanics. But it's not just about the sun. Venus's atmosphere plays a significant role in this cosmic slow dance. The thick atmosphere of Venus generates something akin to an atmospheric tide. This is due to the heating and cooling cycles that occur as different parts of Venus face the sun. Imagine this. When the bright side of Venus faces the sun, it heats up. This heating causes the atmosphere to expand and rise. Conversely, the dark side cools, causing the atmosphere to contract. This constant expansion and contraction exert a subtle pressure on Venus's surface, further contributing to its slow rotation. It's like a planetary heartbeat, steady yet slow. Scientists think that in the distant past, Venus might have spun differently, maybe even faster. Over eons, these tidal forces and atmospheric tides have acted like a cosmic braking system. As we marvel at this cosmic choreography, we are drawn into deeper questions about Venus's past and future, an invitation to explore further the intricate dances of our universe. Venus, the planet closest to us in size and position, harbors secrets about its past rotation that are both puzzling and intriguing. Unlike Earth, which spins once every 24 hours, Venus completes a full rotation only once every 243 Earth days. This sluggish pace is a fascinating anomaly in our solar system, inviting us to delve deeper into its origins and evolution. To put this into perspective, imagine a ballet dancer spinning gracefully on one toe. If the dancer's speed suddenly dropped to a crawl, it would alter the entire performance. Similarly, a change in Venus's rotation speed would have profound implications for its atmosphere and climate. Astronomers believe that Venus's thick sulfuric acid clouds contribute to its extreme temperature, which averages around 462 degrees Celsius, 864 degrees Fahrenheit. This scorching heat is a testament to the powerful greenhouse effect created by the planet's dense atmosphere. While Venus does not have a global magnetic field like Earth, it possesses an induced magnetosphere due to interactions between the solar wind and ionized particles in its upper atmosphere. One might wonder how such a massive impact early in Venus's history could have reversed its spin direction. This catastrophic event is believed to have been so powerful that it not only altered the planet's rotation, but also shaped its atmosphere and climate over time. To fully grasp Venus's current state, we must consider its past. The dense sulfuric acid clouds that shroud the planet are a result of complex atmospheric processes that have evolved over billions of years. As we unravel these mysteries, we find ourselves standing at the edge of an even bigger question. What was Venus like before this colossal impact? And how did it shape the planet we see today? Envision a world where the sun rises in the west and sets in the east, where days are longer than years. This is not merely a thought experiment, but a glimpse into the reality of our nearest planetary neighbor. By exploring Venus's past, we gain insights into its present and perhaps even hints about its future. This cosmic dance of the heavens is not just a scientific curiosity, but a testament to the ever-evolving nature of our universe. As we continue to study this enigmatic planet, we may uncover more secrets about its origins and evolution, helping us piece together the cosmic puzzle that is our solar system. The dense clouds of Venus have been observed producing lightning, a phenomenon that hints at the planet's dynamic atmosphere. Future missions aim to delve deeper into these storms and understand their role in Venus's climate. The European Space Agency's Venus Express mission, operational from 2006 to 2014, provided valuable insights into the planet's atmosphere and weather patterns. This orbiting observatory studied how Venus's thick carbon dioxide atmosphere traps heat, creating a runaway greenhouse effect that raises surface temperatures to extreme levels. Despite the challenging conditions on Venus, future missions are planned to explore this environment further, hoping to shed light on the planet's unique climate and rotation. The Pioneer Venus mission in 1978, with its orbiter and atmospheric probes, was a groundbreaking endeavor that paved the way for subsequent studies. These missions have given us invaluable data about Venus's atmosphere and its impact on the planet's extreme temperatures. As our understanding grows, so does our curiosity about this enigmatic world. Each new discovery brings us closer to unraveling the mysteries of Venus and its place in our solar system. Future missions hold promise for even greater insights as we continue to explore the extraordinary properties of Venus's rotation and climate. Our understanding of Venus is always evolving, much like the planet itself, which holds endless secrets waiting to be uncovered. Think of it this way. Standing on Venus would feel like being a kilometer under the ocean here on Earth. These conditions influence not only the planet's climate, but also its rotation and day length. Understanding this unique environment is crucial for unraveling the mysteries of Venus's past, present, and future. Venus, our closest neighbor in the solar system, receives an extraordinary amount of sunlight. In fact, it's so intense that scientists have measured its solar intensity to be comparable to standing under a magnifying glass. This high level of solar radiation contributes significantly to Venus's extreme surface temperature. To understand why Venus experiences such intense solar radiation, we must look at its albedo, a measure of how much sunlight is reflected back into space. Venus has an unusually high albedo, reflecting about 70% of the incoming sunlight. In comparison, Earth's albedo is around 30%. This means Venus reflects a substantial amount of sunlight back into space, yet still retains enough to create a powerful greenhouse effect. Gaining insight into how intense solar radiation contributes to Venus's slow rotation helps us understand the planet's unique environment and its implications for life as we know it. With this knowledge, we can delve deeper into the mysteries of Venus's past, present, and future. Venus's core composition and its influence on rotation is a mystery scientists have long pondered. Let's delve into the planet's interior to understand what might be driving this celestial oddity. One theory suggests that Venus may have a solid iron core, similar to Earth's. But unlike our planet, it seems this core might be inert. Scientists propose that Venus's core has not undergone the dynamic processes seen on Earth, where the molten outer core generates a global magnetic field through convection. Unlike Earth's churning outer core, Venus's could be more stable and less active, resulting in a lack of the strong magnetic field we experience. This stability might also impact the planet's rotation rate. A less active core means less internal heating and energy redistribution within Venus. The mantle dynamics of Venus are another area of intrigue. Unlike Earth's active plate tectonics, Venus appears to have a single immobile crust. This lack of movement could contribute to the planet's slow rotation. With no plate tectonics, there might be less energy being dissipated and recycled back into the core. Another key point is Venus's magnetic field or lack thereof. Unlike Earth, Venus doesn't generate a strong global magnetic field. This interaction is a far cry from Earth's dynamo effect, where the spinning core generates a powerful magnetic shield. Connecting these dots, we see that Venus's internal structure may directly influence its slow rotation and the unique day-night cycle it experiences. The calmness of its core and mantle, combined with the absence of a strong magnetic field, paints a picture of a planet in equilibrium that favors stability over change. As we continue to unravel the secrets of Venus, these insights highlight the profound influence a planet's interior can have on its most visible characteristics. This extended day-night cycle poses intriguing challenges for any hypothetical life forms that might exist on Venus. Extremophiles, organisms capable of thriving in extreme environments, offer a glimpse into the possibilities. These hardy microbes can withstand conditions that would be lethal to most life forms on Earth, raising hopes for potential habitability zones on Venus. However, the intense heat and pressure on Venus's surface presents significant barriers to life as we know it. Scientists speculate that any life forms would need to dwell in the upper layers of the atmosphere, where conditions are less harsh. The dense clouds composed of sulfuric acid might harbor microbes that have adapted to survive in this toxic environment. Imagine tiny, resilient organisms suspended within these clouds, enduring the extreme conditions with remarkable tenacity. As we ponder these possibilities, it's essential to remember that our understanding of life is limited to what we have discovered on Earth. The implications of Venus's unusual day-night cycle on potential life forms are both captivating and humbling. While Venus's day-night cycle is a captivating puzzle, it's far from the only celestial factor shaping its habitability. The Sun, Earth, and even Jupiter exert gravitational influences on Venus, creating tidal forces that can subtly alter its rotation over time. These forces act like a giant hand, nudging and pulling on Venus's surface to gradually slow its spin. Over eons, these gravitational interactions have brought Venus to a state of tidal locking. This is similar to how the Moon's rotation has been captured by Earth's gravitational pull, always showing us the same face. But unlike our satellite, Venus isn't tidally locked in a way that keeps one side permanently facing the Sun. Instead, it experiences a process called pseudo-synchronous rotation. This means Venus's spin is slowed down by the Sun's tidal forces, but it doesn't completely stop like the Moon. The result is a complex dance of rotation and orbit, deeply influenced by the solar system's gravitational ballet. As we marvel at the complex dance of Venus's rotation and its orbit, we must consider another vital factor in this cosmic ballet: volcanic activity. Venus is not merely a passive participant in the gravitational waltz of the solar system, it is an active world with its own geological forces at play. The surface of Venus is marked by vast volcanic plains and towering shield volcanoes, a testament to its fiery past. Among these, the Ma'at Mons is particularly notable, stretching over 740 kilometers across the surface and rising to a height of 5 kilometers. These volcanic eruptions can shape the planet's crust and potentially influence its core, which in turn affects Venus's rotational speed. The frequent volcanic eruptions on Venus may have the power to alter the planet's surface temperature and pressure, impacting its overall rotation. Imagine lava flows that could stretch for hundreds of kilometers, altering the landscape and potentially creating new stresses within the planet's interior. These eruptions can release vast amounts of heat and pressure, temporarily altering the balance that governs Venus's rotation. While we don't yet fully understand all the factors influencing Venus's slow spin, volcanic activity is a seldom discussed factor that warrants closer examination. In the vast cosmic dance of Venus's rotation, the fire and fury of its volcanoes add a dynamic layer that is both awe-inspiring and intriguing. The result is not just a passive planet orbiting the Sun, but an active world with its own internal forces shaping its rotation and evolution. As we continue to explore the mysteries of Venus's volcanic past, we may uncover new insights into how its fiery nature influences its celestial waltz. This makes the surface temperature on Venus scorching hot, over 864.62 degrees 6 Celsius. To put that into perspective, it's hot enough to melt lead. The thick atmosphere causes another peculiar effect. It creates a massive pressure at the surface. This extreme pressure adds to the challenges for potential life forms on Venus. And if that weren't enough, Venus lacks a global magnetic field. This lack of a protective magnetic field exposes Venus to harsh solar winds and cosmic rays, making it even more inhospitable. So, when we think about the climate of Venus, it's not just the heat, it's also the intense pressure and lack of magnetic protection. And all these factors come together to create a climate that's incredibly challenging for life as we know it. On Earth, we know there are organisms called extremophiles that can survive and even thrive in the most challenging conditions. Some of these life forms can withstand temperatures as high as 251 degrees Celsius, 207 degrees Celsius. If such hardy organisms can exist on our planet, could similar forms be present on Venus? Another fascinating possibility is life within Venus's subsurface oceans, if they exist. Water vapor has been detected in the upper atmosphere of Venus, suggesting that water might be present beneath the surface. If so, these oceans could harbor unique life forms adapted to high pressures and temperatures. To survive in such extreme conditions, these hypothetical organisms would have developed specialized strategies. They might possess heat-resistant proteins or unique metabolic processes to tolerate the scorching temperatures. Imagine microorganisms that can break down sulfuric acid for sustenance, or bacteria that use lightning strikes as a source of energy. The possibilities are endless when we consider the vast array of extremophiles found on Earth. Venus's extreme environments present an intriguing scenario for life as we know it. While we have yet to discover any concrete evidence of such organisms, The search continues to be one of the most exciting and challenging endeavors in astrobiology. As we deepen our understanding of Venus's harsh conditions and the ingenious ways extremophiles can adapt, we come closer to unraveling one of the greatest mysteries of our universe, the potential existence of life in extreme environments. But what truly sets Venus apart is its day-night cycle. During this long day, the thick atmosphere absorbs and retains heat from the sun. As a result, there is little variation between day and night temperatures on Venus's surface. The extreme conditions created by this atmosphere make it one of the harshest environments in our solar system. Understanding these properties brings us closer to unraveling another great mystery: what life forms could potentially survive in such extreme environments. The solar wind is a stream of charged particles that flows outward from the sun. When these particles interact with Venus's ionized atmosphere, they induce a weak magnetic field around the planet. This induced magnetosphere is quite weak compared to Earth's powerful magnetic shield. For comparison, imagine trying to block a strong gust of wind with just a thin sheet of paper. The lack of a global magnetic field on Venus might seem inconsequential at first glance, but it has profound implications for the planet's rotational dynamics. The absence of a strong internal magnetic field means that Venus is more susceptible to external forces like the solar wind and tidal forces from the sun. And this insight extends beyond Venus itself, offering a glimpse into the complex interplay between magnetic fields and rotational stability across the cosmos. The tectonic activity on Venus is a key factor influencing this extended rotational period. Unlike Earth, which has plate tectonics driven by heat from its core, Venus's heat distribution is less efficient due to its slow rotation. These lightning events suggest that there is more going on beneath the dense cloud layer than meets the eye. Tectonic activity, though less pronounced than on Earth, plays a significant role in shaping Venus's surface and influencing its rotation. While the exact mechanisms of Venus's tectonics are still being studied, there is no doubt that these forces contribute to maintaining planetary stability over vast timescales. This geological stability is crucial for understanding the factors that shape Venus's rotational speed and its unique place in our solar system. This continuity across centuries and even eons underscores the enduring nature of our celestial neighbors. Despite their vast differences from Earth, planets like Venus offer unique insights into the fundamental workings of our cosmos. Understanding Venus's tectonic activity and its implications on the planet's rotation helps us piece together the intricate puzzle of our solar system. Perhaps most importantly, these explorations serve as a reminder of the vastness and complexity of our universe. Venus is a peculiar planet, not only for its dense atmosphere and scorching surface temperature, but also due to its unique rotation cycle. In comparison, Earth has an axial tilt of about 23.5 degrees. This difference in orientation dramatically affects how sunlight is distributed over the course of a year. On Earth, seasons are created by this axial tilt as it causes the amount of sunlight received to vary throughout the year. But on Venus, this variation is minimal. The nearly vertical axis of Venus means that the sun's rays hit the surface at almost the same angle throughout the year, leading to very little change in daylight hours or solar heating. As a result, Venus experiences only minimal temperature variations across its surface throughout the year. This extreme heat is further exacerbated by the planet's slow rotation and dense atmosphere that traps heat efficiently. Imagine trying to cool down a greenhouse on a hot day without opening any windows or doors. That's essentially what Venus is experiencing. The combination of a minimal axial tilt and a slow rotational period means that heat distribution on Venus is highly inefficient. This inefficiency further impacts the planet's climate and any potential for life as we know it. Imagine trying to keep track of time in such a world. No rush, just patience as the celestial body makes its slow dance. With such a sedate pace, it's no surprise that this slow spin contributes to Venus's extreme temperature. Heat distribution is less efficient on slower rotating planets, trapping warmth in the dense atmosphere. Let's consider the lava plains, vast expanses of molten rock that make up a significant portion of Venus's surface. These desolate landscapes form when volcanic activity bubbles to the surface, spewing lava in all directions. Over time, these eruptions shape smooth, featureless expanses, frozen in place by Venus's slow rotation. Now let's talk about impact craters, those circular depressions caused by meteorite strikes. On Venus, these craters are remarkably well preserved due to the planet's sluggish spin. Unlike Earth, where weathering and tectonic activity quickly erase crater marks, Venus's static surface keeps them intact for millions of years. Finally, consider the coronae, those peculiar concentric rings that appear around certain impact sites. These patterns form when ejecta from a meteorite strike is blown outward, creating a ring-like structure. Venus's lack of plate tectonics and weathering ensures these unique features remain visible on the surface. Understanding how Venus's sluggish spin shapes its surface gives insight into how life might interact with these unique features. Venus's cloud cover is unlike anything seen on Earth, a thick blanket of sulfuric acid and other compounds that perpetually obscure the surface. As the planet spins in its unusual retrograde rotation, these clouds exhibit their own peculiar behaviors, shaped by the slow, backward motion of Venus itself. The slow spin of Venus results in a phenomenon known as superrotation. This means that the clouds on Venus can whip around the planet at speeds much faster than the planet's rotation. The highest winds reach up to 224 miles per hour, sculpting the cloud cover into complex patterns. These winds create a dynamic atmosphere where clouds can form and dissipate rapidly. The sulfuric acid droplets that make up the clouds are constantly shifting, leading to a cloud cover that is in constant flux. As these sulfuric acid droplets rise and fall within the atmosphere, they absorb sunlight and re-emit it back into space, a process known as infrared radiation. This further contributes to the planet's extreme greenhouse effect. The slow retrograde rotation of Venus also means that sunlight hits different parts of the planet at varying intensities throughout the day. This uneven distribution of heat can lead to more pronounced weather patterns and even larger storm systems. Imagine a world where the wind could carry sulfuric acid droplets over vast distances in mere hours. Such is the reality of Venus's cloud cover, shaped by its slow yet powerful retrograde spin. This unique atmospheric environment could host life forms unlike any on Earth. Adaptations might include rapid dispersal mechanisms or specialized light-absorbing structures to harness the planet's perpetual sunlight. With each discovery, our understanding of Venus deepens. As we unravel the secrets of its cloud cover and rotation, we gain insight into how life might thrive in this otherworldly realm. The next time you gaze at the night sky, remember that beneath Venus's thick cloud cover lies a world shaped by forces unlike any on Earth. Beneath the thick cloud cover of Venus, a unique phenomenon takes place: superrotating winds. Imagine the winds swirling in a tight circular motion, completing an entire rotation every 4 Earth days. On Venus, the atmosphere does not rotate with the planet's surface, but instead moves in a superrotation. The cause of this superrotation lies in the planet's retrograde spin and its dense atmosphere. This unusual spin direction, combined with the planet's dense atmosphere, creates conditions that allow for these super-rotating winds. This trapped heat influences global wind patterns, creating conditions that could potentially harbor unusual life forms. Understanding these atmospheric conditions is key to exploring the possibilities of life in such extreme environments. To put this into perspective, it's equivalent to being 1 kilometer under the ocean on Earth. This extreme pressure is a result of Venus's slow rotation and its thick atmosphere. This backward spin contributes to the planet's extreme temperature and inefficient heat distribution. The slow rotation rate also means that Venus experiences less variation in sunlight throughout its year. Yet, the resilience of microorganisms here on Earth gives us a glimmer of hope that some form of life could exist in these harsh conditions. The slow rotation of Venus has some fascinating consequences on its atmosphere. A phenomenon known as superrotation is one of the most striking effects. The thick clouds of Venus are not stationary. They move rapidly across the planet's surface. This is because the upper atmosphere of Venus rotates much faster than the planet itself. Scientists estimate that at certain altitudes, the atmosphere can complete a full rotation in just 4 Earth days. That's more than 60 times faster than the planet itself. These high-speed winds are a direct result of the heat from the sun warming the atmosphere differently at various latitudes. The intense heat creates pressure differences that drive these atmospheric tides and winds. This rapid superrotation has a profound effect on the weather patterns of Venus, creating unique cloud movements that we don't see on Earth. Despite its slow rotation at the surface, Venus's atmosphere is incredibly dynamic due to this superrotational effect. The implications of these atmospheric dynamics are far-reaching. They show how even in extreme conditions, like those on Venus, certain phenomena can arise that challenge our understanding of planetary weather. This dynamic environment also provides insights into the potential habitability of planets with similar conditions. If life exists on Venus, it would need to adapt to this rapidly changing atmosphere. It's the polar vortices of Venus that make this planet's weather patterns so unique and extreme. With such intense pressure, the air becomes incredibly dense, creating these powerful vortices. These vortices play a crucial role in Venus's atmospheric circulation. These high-speed winds sweep across the planet's surface, causing dramatic weather changes. Despite these intense conditions, Venus's retrograde rotation can create some unexpected behaviors. The dense atmosphere traps heat from the sun, contributing to Venus's extreme temperatures. Any potential life forms on this planet would need to adapt to these rapidly changing conditions. As these vortices sweep across the surface, they create a dynamic environment that is constantly in flux. This rapid change could have profound implications for any hypothetical life forms trying to survive. But it's not just the winds. The thick clouds of sulfuric acid also play a role in shaping this harsh climate. Understanding these weather patterns gives us a glimpse into the potential habitability of Venus and how life might adapt to such extreme conditions. The relationship between Venus, the Sun, and Earth can be understood through a simple analogy. Imagine 2 dancers in a slow waltz, their movements guided by an unseen partner. In this scenario, Venus is one of the dancers, the Sun is the other, and Earth plays the role of the unseen partner orchestrating their movements from afar. The gravitational interactions between these celestial bodies create a delicate balance that has shaped Venus's rotation over time. As the dancers continue to move in their waltz, they occasionally come into closer contact with one another. These moments of proximity can cause slight variations in their dance, much like how the Earth's gravity can slightly influence Venus's rotation during periods when the 2 planets are closer together. However, these interactions are subtle and do not significantly alter the overall equilibrium established by the Sun's gravitational pull. Despite the stability of this celestial dance, it is possible that future changes in the Earth-Sun system could impact Venus's rotation. For example, if the Sun were to expand into a red giant star, or if Earth's orbit shifted dramatically, these events could potentially disrupt the delicate balance that maintains Venus's current rotation period. However, such scenarios are far off in the future and would take billions of years to unfold. For now, we can marvel at the intricate ballet performed by Venus, the Sun, and Earth, with each celestial body playing its part in shaping the planet's rotation. The gravitational interactions between these bodies have created a unique dance that has allowed Venus to maintain its slow spin for billions of years. This understanding not only highlights the beauty of our solar system, but also emphasizes the importance of studying gravitational forces in the context of planetary habitability. With this understanding, we can appreciate the complex interplay between Venus and its celestial neighbors, as well as the role that gravity plays in shaping our solar system. By continuing to study these gravitational interactions, we can deepen our knowledge of planetary habitability and gain insights into the potential for life on other worlds. The impact of Venus's unique properties on human space travel is profound and continues to shape our understanding of the universe. The geological history of Venus is a tale of cataclysmic events and slow-burning changes that have shaped its unique rotation. Early in its life, Venus was likely bombarded by comets and asteroids, which could have altered its spin direction and contributed to the planet's retrograde rotation. One significant event was the formation of massive volcanic features, like coronae large, circular plains thought to be remnants of ancient lava flows. For instance, the Artemis corona is a vast plain on Venus, believed to have formed from extensive volcanic eruptions that spread lava over millions of square kilometers. These eruptions could have influenced Venus's crustal stability and the planet's overall rotation rate, as large volumes of lava redistributed mass. Another notable geologic feature is Phoebe, a huge impact crater that dwarfs even the massive basins on Earth's moon. The force of this collision could have altered Venus's spin axis and contributed to its slow rotational period, now longer than its own year. Geological events like these have profoundly influenced not only the surface of Venus, but also its internal structure and rotation dynamics over eons. Understanding these processes is crucial for grasping why Venus's rotation is so unusual and what it means for the planet's potential habitability. As we continue to explore Venus and uncover more about its geologic past, we can piece together the puzzle of how this planet has evolved over billions of years. But what factors contribute to this slow rotation? Scientists point to gravitational interactions with other celestial bodies as a major influence. The Sun, for instance, exerts significant tidal forces on Venus due to its proximity. Over time, these tidal forces can gradually slow down Venus's rotation. Another important factor is Earth's gravitational pull. Although it's much smaller than the Sun's influence, over billions of years these forces can accumulate. Mars also plays a role, albeit a minor one. Its tidal forces are smaller still, but every bit contributes to the complex interplay of gravitational perturbations. These external forces have shaped Venus's rotation over eons. Understanding these gravitational perturbations is crucial for gaining insight into the long-term stability of Venus's rotation. As we continue to study the planet and its environment, we can better predict how these forces will affect Venus over time. This knowledge not only deepens our understanding of Venus, but also provides insights into the broader mechanics of celestial bodies. Ultimately, it's a dance of cosmic proportions shaped by the gentle but persistent tug of gravity. A slow waltz that has been going on for billions of years. Venus's lethargic dance around the Sun is no mere surface show, but a deep, ancient ballet choreographed by its very core. Dive beneath Venus's scorching surface to unravel the mysteries of its interior dynamics, a world hidden from view yet pivotal to its slow waltz through space. At Venus's heart lies a core that, unlike Earth's, is not solid but molten iron, roiling with heat and energy. This fiery core, though smaller than Earth's, plays a crucial role in generating Venus's intense magnetic field. Above this molten heart stretches the mantle, a layer of semi-solid rock that encircles the core like an embrace. The crust, however thin compared to Earth's, is a testament to Venus's unique formation story. Seismic waves reveal that beneath this crust lies a mantle. Unlike any other, it's thicker and less mobile, locked in a slow, sluggish dance. Radar mapping data illuminates the truth. Venus's mantle is not as active as once believed, barely stirring beneath its surface. This languid mantle contributes to Venus's slow rotation, a phenomenon shaped by more than just tidal forces from the Sun. The core's molten state, combined with a thick and sluggish mantle, creates an environment where heat is trapped and movement is minimal. Thus, Venus's internal structure acts like a cosmic brake, slowing its spin in this grand celestial ballet we witness from afar. In understanding these hidden depths, we grasp the true majesty of Venus, a planet that dances to the rhythm of its own deep heartbeat. And as it continues this ancient dance, we are left in awe of the cosmic forces that shape our universe's most enigmatic bodies. But what makes Venus's climate so uniquely harsh? Part of the answer lies in its peculiar rotation. Venus has a phenomenon known as superrotation. Its atmosphere whips around the planet in just 4 Earth days, much faster than Venus itself rotates on its axis. This super-rotating atmosphere affects the distribution of heat and wind patterns on Venus. But unlike Earth, where winds help distribute heat more evenly, Venus's superrotation causes the atmosphere to circulate so quickly that it doesn't effectively spread out the heat. This is due to a combination of factors including Venus's slow rotation and the atmospheric tide created by the heating of its atmosphere. The result is a planet with an incredibly uneven temperature distribution. Additionally, Venus's superrotation can create extreme wind patterns at high altitudes. As we continue to study Venus, we gain a deeper understanding of how its unique atmospheric conditions contribute to these rotational characteristics and potential climate stability. During this time, sunlight varies significantly across the planet. The thick atmosphere of Venus scatters and reflects much of the incoming sunlight, creating a uniform twilight-like condition. Given these extreme conditions, it's difficult to imagine how any life form could adapt and thrive on the surface of Venus. But understanding these rotational characteristics and atmospheric conditions is crucial as we continue to explore the possibilities of life in our solar system. It allows us to appreciate just how delicate and specific the conditions are that support life as we know it. As we delve deeper into Venus's day-night cycle and its implications, we begin to understand the true marvel of our own planet's ability to support life. This deepens our awe and respect for the incredible diversity of conditions that make up our cosmic neighborhood. While Earth and Venus orbit the Sun at different speeds, there's a unique relationship between them called orbital resonance. During this time, the Sun would rise and set twice in one Venusian day because of how slowly it rotates. Meanwhile, Earth whizzes around the Sun every 365 days, about 1.5 times faster than Venus. Over time, these forces have slowed down Venus's rotation rate significantly. So much so that if you were to stand on the surface of Venus and watch the Sun rise, it would be over 117 Earth days before it set. This extraordinary orbital dance is what makes Venus's rotation so fascinating and unique among the planets. But while this resonance creates a beautiful rhythm in space, it also has profound implications for life as we know it. Venus's rotation is governed by powerful tidal forces, with the Sun exerting its gravitational pull on the planet. The slow rotation of Venus means the Sun rises in the west and sets in the east, a unique rhythm shaped by these celestial forces. But tidal forces aren't limited to the Sun alone. Other planets also play their part in shaping Venus's environment. The closest approach of Earth and Venus exerts a noticeable pull, while the distant Jupiter has its own subtle influence. These combined tidal forces have shaped Venus's atmosphere over time, contributing to its extreme pressure and temperature. The intense solar wind has gradually stripped away lighter elements from Venus's upper atmosphere, a process accelerated by these same tidal forces. The surface of Venus bears the marks of this cosmic tug-of-war, with geological features like volcanoes and tectonic patterns shaped by these relentless forces. These external influences remind us that Venus, despite its isolation, is part of an intricate cosmic dance governed by unseen gravitational forces. The atmosphere of Venus is divided into several distinct layers, each with its own unique properties. Closest to the surface is a region known as the twilight zone, where temperatures can soar as high as 250 dC to 480 degrees Celsius. This layer serves as a crucial buffer between the scorching surface and the cooler regions above. Above the twilight zone lies the daylight zone, where temperatures drop to around 135 degrees C to 75 degrees Celsius. This layer is bathed in perpetual sunlight due to Venus's slow retrograde rotation and thick cloud cover. The winds here blow with incredible ferocity, reaching speeds of up to 360 kilometers per hour, 224 miles per hour, at the planet's equator. The uppermost layer of Venus's atmosphere is known as the night-side zone. This region experiences temperatures that can dip as low as 123 degrees Celsius to 225 degrees Celsius. The stark contrast in temperature between the surface and the night-side zone creates a powerful atmospheric tide, further influencing Venus's rotation. Clouds on Venus are another critical factor in its atmospheric dynamics. The planet's dense atmosphere is blanketed by thick, sulfuric acid clouds that reflect much of the incoming sunlight back into space. These clouds move with the winds at different altitudes and help to maintain a stable temperature across the surface. In the grand tapestry of Venus's atmospheric dynamics, every aspect works in harmony to create a planet that is both mysterious and extraordinary. Despite its extreme conditions, Venus offers a window into the intricate workings of our universe and the forces that shape it. As we continue to explore this enigmatic world, each discovery reveals another thread in the cosmic dance, guiding us toward a deeper understanding of our universe's vast and complex wonders. Imagine Venus's atmosphere like a giant wheel slowly turning in one direction, while the planet itself turns in the opposite way. The result is an intricate dance between the planet's surface and its thick cloud cover. The retrograde rotation has profound effects on Venus's environment and potential habitability. The perpetual sunlight and extreme heat due to the runaway greenhouse effect make conditions inhospitable for life as we know it. This unique spin not only affects Venus's climate, but also its ability to maintain stable temperatures suitable for life. The slow rotation means that the same side of Venus always faces the sun, making one hemisphere unbearably hot while the other remains in perpetual darkness. The implications are stark. While Venus might have once been habitable billions of years ago, its current conditions are far from suitable for life as we know it. The extreme temperatures and perpetually sunlit side make it a place where no known Earth-like organism could survive. As we explore the cosmic dance between Venus's rotation and its environment, it becomes clear that this enigmatic world offers more questions than answers. Understanding the intricate balance of its retrograde spin and atmospheric tides may one day help us unravel the mysteries of our universe's vast and complex wonders. Venus, the hottest planet in our solar system, is known for its unique retrograde rotation. This unusual spin direction means that if you were standing on Venus's surface, you would see the sun rise in the west and set in the east. This backward motion is believed to be a result of an ancient collision that altered the planet's spin direction. But what makes this retrograde rotation even more intriguing is its influence on Venus's volcanic activity. Scientists have found that the slow rotation of Venus, combined with the planet's intense internal heat, leads to an interesting phenomenon: vast lava oceans. Imagine molten rock flowing like a sea across Venus's surface. This is due to the planet's slow rotation, which allows magma to spread out and cool down slowly, creating expansive lava plains. The lava oceans on Venus are so vast that they could potentially cover entire continents on Earth. This is a testament to the sheer scale of volcanic activity on this planet. But how does this slow rotation and intense volcanism influence Venus's overall surface conditions. The lava seas on Venus contribute to the planet's extremely high temperatures. As magma flows and cools, it releases a tremendous amount of heat into the atmosphere. This constant influx of heat further exacerbates Venus's greenhouse effect, making its surface one of the hottest in our solar system. Additionally, the slow cooling of these lava oceans can lead to the formation of unique geological features. As magma solidifies, it creates complex landscapes that are unlike anything found on Earth. So, the next time you think of Venus, picture not just a scorching hot planet, but one where lava oceans flow and shape its surface in ways we are only beginning to understand. And as you drift off to sleep, let the awe-inspiring image of Venus's lava seas settle your mind. Venus's slow rotation has profound effects on its atmospheric chemistry. This slow spin leads to inefficient atmospheric mixing and unique chemical reactions driven by sunlight. These reactions are influenced by the planet's slow rotation, which affects how sunlight interacts with the atmosphere over time. Understanding how rotation affects the chemistry of an atmosphere is crucial for assessing the potential habitability of a planet like Venus. The slow rotation of Venus results in atmospheric tides that can further complicate the chemical equilibrium of its atmosphere. This interplay between rotation, sunlight, and atmospheric chemistry is part of what makes Venus so unique in the solar system. As you drift off to sleep, let the complex dance of rotation and chemistry on Venus fill your thoughts with a sense of cosmic wonder. Venus, the second planet from the Sun, is known for its slow and peculiar rotation. This unique spin is shaped by a combination of factors, including the gravitational influence of the Sun. One significant factor affecting Venus's rotation is thermal tides, the rise and fall of its atmosphere caused by solar heating. Every day on Venus, as the Sun rises, it heats the atmosphere unevenly, causing a shift in the planet's mass distribution. This thermal effect creates a type of atmospheric tide that pulls on Venus, affecting its rotational speed and axis tilt. The Sun's heat not only influences the temperature, but also contributes to the planet's slow rotation by creating these thermal tides. To put it in perspective, imagine a gentle breeze that gradually slows down a spinning top. That's what the thermal tides do to Venus. The result is a complex interplay of forces that shape Venus's unique rotational dynamics, a fascinating dance between gravitational and thermal influences. Rest assured that the complex dance of rotation and chemistry on Venus continues to unfold in the vast expanse of our cosmic neighborhood. And as you drift into dreams, remember that the universe is filled with such wonders waiting to be discovered. At the heart of Venus's slow rotation is Mercury, our solar system's smallest planet. Despite its size, Mercury exerts a significant gravitational pull on Venus. Over long time scales, this interaction subtly influences Venus's rotation. Imagine Venus and Mercury as two dancers in a cosmic ballet. As they orbit the Sun, their gravitational fields ebb and flow, tugging at each other like partners in a dance. The result is a delicate balance, a state of equilibrium where the forces from the Sun and Mercury keep Venus's rotation in check. It's this complex interplay that has led to Venus's unique rotational period. Now, imagine if you could travel through time and observe these celestial bodies thousands of years ago. How different might their dance have been? The interaction between Mercury and Venus is a testament to the ever-evolving nature of our cosmos. And as you settle into a calm night's rest, let the knowledge that these celestial interactions have been shaping our cosmos for eons fill you with a sense of awe and wonder. But to truly understand the conditions on this enigmatic planet, we must delve beneath its surface and explore the extraordinary properties of its core. These electrical disturbances provide a glimpse into the planet's complex internal dynamics. At the heart of Venus lies its core, a dense metallic region that influences the planet's rotational behavior. Such an unusually slow rotation period is shaped by the planet's core composition and density. The density of Venus's core plays a critical role in determining how efficiently heat is distributed within the planet. Imagine your body as a massive structure, and every second you move just a fraction of an inch. That's the pace at which Venus rotates. Understanding the core's composition and its impact on Venus's dynamics helps us paint a clearer picture of the conditions that might have affected potential life forms on this planet. For in exploring this enigmatic planet, we are reminded of the vast and fascinating mysteries that our universe still holds. But it's not just CO2 that makes up Venus's skies. Clouds of sulfuric acid droplets float within this atmosphere, creating a toxic brew unmatched in our solar system. The slow retrograde motion causes heat to be trapped more efficiently, contributing to Venus's extreme temperatures. But how does this thick, toxic cloud layer form? The answer lies in the planet's unique rotation. The intense sunlight on one side of Venus creates powerful winds that whip around the planet at high speeds. These supersonic winds then heat the atmosphere, creating a tidal effect that slows down Venus's rotation even further. The constant heating and cooling of the atmosphere lead to the formation of sulfuric acid clouds. This atmospheric toxicity is a stark reminder of how the unique properties of Venus's rotation make it one of the most inhospitable planets in our solar system. The dense, sulfuric acid clouds combined with high levels of carbon dioxide create an environment where life as we know it would struggle to survive. From Earth, we gaze at this distant world, knowing that under its shroud of sulfuric acid and CO2, Venus harbors no secrets of life as we understand it. But here's where it gets interesting. Venus doesn't just spin backwards compared to most planets. It also has the slowest rotation of any planet in our solar system. This slow retrograde motion means that solar eclipses happen with unusual frequency on Venus. While Earth experiences a total solar eclipse roughly every year and a half, on Venus they occur about twice as often. Imagine living in this world where the sun's dance with its orbiting planet is not just an occasional spectacle, but a regular feature of the sky. Now, think about how this unusual rhythm might affect any potential life forms on Venus. While the slow rotation could create a more stable environment, the frequent solar eclipses add another layer of complexity. These regular celestial events might influence the development of photosynthetic life, if any were to evolve under Venus's thick atmosphere. It's a stark reminder that even the most basic aspects of our planetary neighbors can have profound implications for how life might or might not emerge in their worlds. And as we stand back and observe this cosmic ballet, we're left with a sense of the universe's rich tapestry, where even the slowest dance can hold hidden wonders. From Venus's slow rotations to its frequent solar eclipses, each piece contributes to a deeper understanding of our cosmic neighborhood and the myriad possibilities within it. Venus's atmosphere is a dynamic system of winds that create a complex web of circulation patterns. These atmospheric winds transfer heat from the planet's surface up to higher altitudes, where it can dissipate into space. These powerful winds play a crucial role in Venus's climate by transporting heat from the scorching surface up into the cooler atmosphere. The complex interplay between these winds and Venus's slow rotation raises intriguing questions about how they might influence the planet's climate and surface conditions. Scientists suspect that these winds might contribute to the planet's runaway greenhouse effect by efficiently redistributing heat. In essence, Venus's atmospheric winds are not just passive observers of the planet's extreme conditions. They actively shape and maintain them. As we explore these wind patterns further, we gain a deeper understanding of how Venus's unique climate and surface conditions are sustained. This interplay between wind patterns and rotational dynamics holds profound implications for our understanding of Venus's climate and the potential for life as we know it. Exploring these atmospheric winds and their role in shaping Venus's climate is a crucial step towards unlocking the mysteries of our cosmic neighborhood. Venus's slow rotation rate of 242 Earth days is not merely a curiosity, but a crucial factor shaping its atmospheric dynamics. A significant aspect of these dynamics are the unique atmospheric currents caused by Venus's slow spin and intense heat. The extreme temperatures on Venus lead to massive pressure differences across its surface, driving powerful winds that can reach speeds of up to 224 mph, 360 km/h. These winds, akin to jet streams on Earth but far more intense, play a crucial role in shaping Venus's climate. The slow rotation also results in an unusual atmospheric tide, influenced by the sun's heating of the thick atmosphere. This tidal force further impacts the planet's rotation rate and overall climate stability. Such intense atmospheric activity underscores the challenges for any potential life forms to exist on Venus. While Earth takes about 24 hours to complete one rotation, Venus, our nearest planetary neighbor, follows a very different dance. It spins in the opposite direction, known as retrograde rotation, and at an excruciatingly slow pace. Imagine if the sun only rose once every 1/17 of our Earth days. That's what inhabitants of Venus experience, a slow, laborious cycle that distributes heat and light unevenly across its surface. This extreme imbalance in the distribution of sunlight affects where life might potentially exist on Venus. While the days are long and nights are short, the intense heat generated by Venus's thick atmosphere could make any attempt at photosynthesis a challenge. Yet, there's a fascinating caveat. The slow rotation allows for the possibility of twilight zones, areas that experience neither full day nor complete night, but rather a perpetual dawn or dusk. These regions might just hold the key to life, as we don't know it. Understanding how retrograde rotation impacts habitability broadens our perspective on potential Venusian life forms. It may be that the unique conditions created by this slow, backward spin open up new possibilities for life to thrive in ways we've never imagined.